So they will move back
Should we
up?
ask why?
There were people who had the rooms booked from another group.
There's the Filipino Student Association, there's the Asian American Student Association.
I knew it would be a good story.
Oh, you registered. The next speaker is Kevin Keating, and his talk is extensions of local fields and elementaries and polynomials.
Yeah, so first, happy birthday. So, also, let me know, this is a very passionate topic. Yeah, so what I have is what I think is an interesting question, and I have a conjecture on the answer for at least some cases, and I have an even smaller subset where I'm actually proving. Okay, so that's what I need to do. So first, I want to introduce the basic notation for local fields. So, well, evaluation of the field K, and then the residue field is perfect, so I guess implicitly I'm assuming it's characteristic P. Yeah, so then you have the integers K, which is all the things with evaluation greater than or equal to 0. And then you have a uniformizer for O sub K, which is something with valuation 1. And then O sub K, the ring of integers, is a local ring. Its unique maximal ideal is generated by the uniformizer. And then, in addition to that, I want to have a finite separable extension of K, which I'm going to call L. And so, say it's totally ramified means that the residue field of L, which is O sub L mod M sub L, is isomorphic to residue field of K, which is O sub K mod M sub K. Okay, so yeah. So anyways, that's the basic notation. Yeah, and so then what I want to do is I want to connect this with symmetric polynomials. Well, actually, this is all well known, of course. So what I have right here is the definition of the C elementary symmetric polynomial in n variables. So you take all possible products of C distinct variables and add that all together. Okay. Yeah, so I guess, originally this lives with coefficients in Z, but ultimately we're going to be viewing it inside of K. So, yeah, so then I'm going to define, using S sub C, a function from L to K, which maps alpha from L onto E sub C evaluated at the various embeddings of alpha into a separable closure of K. Okay, so you have sigma 1 through sigma n of K embeddings of L into K set, and then you evaluate there. And so, for instance, E sub 1, the first symmetric polynomial, is just the sum of variables x1 through xn. So that means that S sub 1 of alpha is just a trace. And then E sub n, so n is supposed to be 3 of L over K. So that means that what we're going to get is the product. And that means that S sub n of alpha is the norm of alpha. Okay, and then, of course, this is the basic fact, which is that if you have L is generated over K by alpha, so alpha is a primitive element for L over K, then the minimum polynomial for alpha over K can be expressed in terms of the S sub C of alphas. Okay, so that's of course well known. So then, here's my problem that I want to consider is I want to determine what S sub C and now to the R. So basically I'm going to apply this symmetric polynomial to conjugates of elements of the rth power of the maximal ideal of F. Okay? Yeah, so actually, well, this problem is too hard for me because S sub C of M sub L to the R is usually not an ideal. So for instance, if you're looking at the case where C is N to be agreed with the extension, then basically you'd be doing class field theory for the extension L over K. I don't want to try to deal with anything that difficult. So what I do instead is look at the easier problem, which is to determine the ideal generated by the image of M sub L to the R under S sub C. Okay, so that's going to be some power of the maximal ideal of K. Okay. Yeah, so can rephrase this problem as a function from the positive, non-negative integers to non-negative integers, where g sub c of r is the smallest valuation of s sub c alpha as alpha raised over m alpha. So this is, h should be the same as g sub c of r here. Okay, that's obviously equal. Okay, so I guess a very easy case is the case where looking at s of n, n is degree of L over k, so therefore s of n is the same as taking the norm, and of course the norm of ml to the r is k to the r, so this is because we're assuming that L over k is totally ramified. So therefore g sub n of r is r. Okay, and of course it is sort of a fundamental part of algebraic number theory that s sub 1 trace is also well understood. So let me do something about that. Yeah, so there's something called the different of L over k. So basically this more or less defines the different, which is that the trace of the inverse of the difference is contained in O sub k, but the trace of ml to one more negative power is not contained in O sub k. Okay? And so using this, and this right here, this is an argument that's sort of classical, it's Sarah's book about vector fields. What you have is that the trace of m sub L to the r is contained in m sub k to the h. So basically think of r and h as just being variables, so it's not negative integers. This is equivalent to, you just move the m sub k to the h over to the left, and then you can move the mk to the negative h inside because the trace is table here, and then you can turn m sub k to m sub L raised to the degree of the extension, so you get this. And then because of this condition right here, this is equal to this inequality, this is equal to this inequality, and so therefore what you get is that the trace of m sub L to the r is actually equal to m sub k to this particular number, so therefore g sub 1 of r is the floor of r plus b over n. So this is, yes, I think in Sarah's book he actually just does it for extensions of prime degree, but the exact same argument works in general. Okay, so that's that. Yeah, so what I want to do now is I want to generalize what we saw in the case of c equals 1 on the previous slide. So to do that, we have to introduce something which is somehow is not so well known even among local field theorists. This is called the indices of inseparability. So this is data that you associate to a totally ramified finite degree extension of local fields. Okay, so what you do is you write down the uniformizer for L, and then you write down its minimum polynomial, which is an Eisenstein polynomial. And I mean, the basis for this is more or less you're going to consider this as giving you a formula which expresses the constant term, which this is an Eisenstein polynomial, is a uniformizer for k in terms of all the other terms here. So so what you do is you look at what happens when you replace x by I sub L. Well, of course, that gives you the entire expression is equal to 0. What you do is you look at the L valuations of the individual terms that you have here. Okay, so, well, what you do then is you define I sub j, and this is, at least in characteristic P, is going to be the jth index of inseparability, to be the minimum of the valuations of these terms that you get by replacing x by pi sub L, is under a restriction, which is that the p-adic valuation of n minus m is less than or equal to j. So that means that n minus m is not divisible by p to the j plus 1. And then there's this shift right in here, which is basically to give you something that's kind of fits in with other data, which we'll see in the next slide. Yeah, so as I said, if characteristic P, these are the indices of inseparability. I guess I should say that somewhere. Yeah, these I sub j is the jth index of inseparability. In characteristic 0, well, you have to do a little bit more finagling. So the problem is that in characteristic 0, different uniformizers can give you different answers here. Whereas in characteristic P, that doesn't happen. So basically, from now on, that will pretty much be assumed definition here, you'll find that I sub nu, so nu is the maximum power of p that divides the degree of extension. That's tested at 0, and then the other indices of separability get larger, but not in a strict sense, except for the first step. Okay, great. Okay, so this is what I have here is the usual ramification data that you have for an extension of local fields. This is the thing that you see in Sarah's book, or you see in Senko and Vistokov, or several other books about local fields. So yeah, okay. So yeah, so first I'm going to define this for a finite Galois extension. So I let G be the Galois group, then you define what's called the T ramification group, lower numbering. Yeah, so the T ramification group for the lower numbering, well, basically what you're doing is you're looking at how far the elements of the Galois group move the uniformizer in a sort of p-adic sense. Okay, so you're basically looking at for sigma, for G sub t, what you're looking at is all of the elements of G which are in some sense sufficiently close to the identity. And that actually forms a subgroup. T I didn't specify to be an integer, and so in fact I want it to be a real number, so that I can now form this integral here, which is the Hasse-Herbron function. So this is the function that you use to translate between the upper numbering and the lower numbering for the ramification groups. Okay, so yeah, so you can also define the Hasse-Herbron function with all lowercase. This cover will not draw a lot. So for that, what we do is G sub G is no longer a group, it's a set of embeddings of L into K, and then E sub L is not evaluation that's not just defined on L, but it's defined on, say, all of a set. And but you still you normalize E sub L so that E sub L cross does give you Z. Okay, so you can essentially do the same definition even if you're not looking at a Galois extension. Yeah, so anyway, so the connection between the indices of separability and the usual ramification data is given by the Hasse-Herbron function is given right here. So basically, you can recover the Hasse-Herbron function from the indices of separability, but as we'll see in the next example, the other direction doesn't work. So you can have cases where the Hasse-Herbron function does not determine all the values of I sub j. Okay. Yeah, so in this example, what I'm going to do is I'm going to let K be just F sub 3 double brackets T, so T is our uniformizer, and then L is generated over K by an Eisenstein polynomial, so therefore automatically L over K is totally ramified to 9. So I want to calculate the indices of separability, so first for that, I'm going to go back to this definition here. So for I sub 0, what we're going to do is we're going to look at the terms in this polynomial here where the power of x is not divisible by p, which is 3 for us. Yeah, so anyways, if you do that, I sub 0, you get is the minimum of the valuation of the x to the 7th term with x replaced by pi l, and then the x to the 4th term, because the other terms have powers of x divisible by 3. So, and then you subtract 9 from this normalization. Basically, that's the subtracting degree of the extension. This is just to get that theorem we had at the bottom of the previous page for expressing the Hasse-Herbron function in terms of the indices of separability. Right? Okay. Yeah. So, anyways, so then you just do the arithmetic and you get 40 for I sub 0. For I sub 1, you're looking at the terms where the power of x is not divisible by 9. So basically, that's everything except the x to the 9th term. And then you do the arithmetic and you get 33. And then for I sub 2, you're allowed to include the x to the 9th term, and then that automatically gives you 0. Okay, so these are the ramification indices of this extension here. rotation indices, and according to that theorem, you get the Hasse-Run function. And so it looks like this. And so this is a case where you can't see what I sub 1 is, even if you have the function, which is the solid line. Okay, so yeah, so finally we get to my conjecture. So what I think is true, so basically what I believe or hope or something is that if you have a polynomial by extension and restricted to degree of power of p, then what I'm claiming is that if you take O sub k times s sub p to the j of ml r, that should be m sub k raised to the ceiling of this index of inseparability plus p to the j times r divided by p to the nu. So p to the nu is the degree of your extension, or equivalently the g sub p to the j of r is given by the exponent there. Okay, so if j equals nu, then this is kind of trivial because the s sub p to the nu is the norm. J equals 0, well, that's s sub p to the 0, which is s sub 1. We already looked at that case. And so what I want to do here is just note that if you look at what we already did, then you'll see that the conjecture is true for j equals 0. Okay, so the difference is generated by f prime of pi I. Okay, so that's somebody else, but number theory, we've seen this many times before. So yeah, the thing is that since I'm assuming a characteristic p, when you take the derivative, terms whose degree is divisible by p give 0 in f prime of x. So basically, we get rid of the terms that we're not supposed to use when we when we calculate I0. So therefore, d can be expressed in terms of I0 this way. Okay, so yeah, so therefore, plugging in this formula for d, which you get, so we knew that g sub 1 of r was r plus d over p to the floor. So we replace d by this formula here, we get this. But then because p to the minus 1 is 1 less than the denominator, this turns into a ceiling function here. Okay, so which is nice and simple. Okay, so I've got 2 minutes, so I'll just say that I can prove the conjecture for nu equals 2. Okay, so basically that's more or less I suppose the fact that it works for j equals 0 plus I suppose j equals nu kind of trivially, plus I can prove it for nu equals 2, so that that's the case j equals 1. That's more or less why I think it's true. Well, about proof, but why do I think the conjecture is true? Well, as I said, suppose j equals 0, j equals nu. I can prove it in characteristic p with nu equals 2. I've looked, using stage, I've looked at some examples where the characteristic of k is 2, and p to the nu is 8, and these also support the conjecture. And then finally, what about characteristic 0? Well, in global fields, it's, somebody can prove a theorem for function fields, and then it's like decades later that the number field version gets proved. That doesn't happen in local fields. If you prove something for the characteristic p case, then the characteristic 0 case is just a matter of technique, but I haven't actually done it. Okay. Yeah. So, anyways, so I guess maybe the last thing I'll say is that why shouldn't I generalize this? Well, this would be what I thought was the obvious generalization. So I get rid of the assumption that the degree of the extensions of power of p, and I also get rid of the requirement that I'm only looking at s of p to the j, but the problem is that doesn't actually work. Okay, so if I take k equals f3 of p and L over k is totally round by 3/4, so this is just a k extension, which is about as simple as you can get in this setting, then this version of the conjecture would predict that s sub 2 of O sub L should give you something that generates O sub k. So yeah, this when I saw this, I thought this was supposed to be the right answer, but apparently it's not. But I think it should be possible to get a version of the conjecture that doesn't assume that ends in power of p, but I don't know what to do about messing with this subscript right here. Okay, so maybe I'll say one more thing, which is that the reason I think this may be interesting or significant is that because the J equals 0 case, I sub 0 is essentially equivalent to knowing what the different of the extension is. So if the conjecture is true, then it might be reasonable to interpret the other indices of inseparability as I1, I2, etc., as being kind of refined or higher order versions of the different or discriminant. And so if you had sort of more data that was kind of like the different or discriminant, then that felt like it should be interesting. Okay.
Are there any questions for us? If not, well, thank you.